Good morning, everybody. Today I'll start the week 4th lecture on fuel firing method and some calculations. Okay, so first fuel. So boiler fuel can be solid fuel or liquid fuel. Solid or liquid fuel. Okay, and solid fuel can be like previous days people are used to use a coal, wood. Okay, many cases those are replaced by liquid fuel, maybe crude oil or heavy fuel, heavy high HD or high viscosity, high density fluid for as a fuel. So those fuel can be given into your furnace along with oxygen and it will be burning. So fuel oil may contain vanadium, sodium, affect superheater, sulfur may contain, so it may contain maybe sometimes sulfur. Okay, sulfur if it is there then you have to reduce amount of sulfur, then you have to use, otherwise sulfur what happens, sulfur plus oxygen it creates sulfur dioxide, again if it gets water, so finally it forms H2SO4, H2SO3. So these are actually harmful gases. So whenever there is any sulfur, you have to take care of all these after combustion effect. If you have some other component, let's say carbon, carbon is a component of fuel. So carbon if not burnt properly, then it will form carbon monoxide. So that is also harmful. So in your combustion system, your main target should be to produce carbon dioxide, not carbon monoxide. Again, you have to avoid the fuel which is having more sulfur or any corrosive component. So those should be avoided. But traces amount of sulfur and other things are there, that one you have to handle separately. Effect of ship design. Effect of ship design on other machinery. Effect of ship design and other machinery on boiler design and other machinery on boiler design. Okay, this portion of this lecture I have taken from marine engineering book by Harrington. Harrington. Okay. So space is the main parameter. So compact space is already better. Okay, because many cases marine ship machinery will not have larger space. Let's say thermal power plant you have on land. So in that case you have lots of space, so you can maintain things properly. But if you have compact space, then everything must be compact. Like your heat exchanger, your turbine system, everything must be compact. So space is one main criteria. Next is a weight and how much energy you are producing, and fuel handling system. So fuel handling system is like when you are moving from one place to another place, you need certain amount of fuel to store. And let's, for example, if you are storing coal, then you have to pulverize or you have to break the coal particle to very small particle, then you can use to your system. If you have liquid fuel, again you have to handle that properly. Again, these are if any fire source is there nearby, that can be dangerous also. So safety and storage is also very important part for shipping machineries. And on generally, larger the physical dimensions of a boiler for a given output, the greater its weight. So larger dimension is obvious, weight will be increasing, and larger dimension maybe it will be for high power systems, for smaller compact system maybe low power systems. So let's say you have initially taken some solid fuel, let's say coal. Okay, now if you want to burn the coal, so it will take longer time. Like you have seen this roadside oven, those people are using coal for their cooking. So coal, it will take longer time. So initially they will be giving some heat, they will be putting some draft air blowing extra, then it will burn. But if you have coal with very small particle size, small size particle, so in this case what will happen, the combustion will be quick. Why it is happening like this? They say I have one bigger particle, diameter d, or radius, let's say diameter d, and I make it to smaller particle, same volume. So small d, same diameter, assume. So pi by 4. So larger particle size is total surface area. So sphere surface area is 4 pi r square, but volume will be 4 by 3 pi r cube. Now if I break it into two, so diameter will be changing. Okay, so volume will be same because total mass is same. So pi by 4 by 3 pi d r cube 2 times equals 4 by 3 pi capital R cube, I can say. So I am getting R equals 2, okay, smaller I will calculate. So I will be getting R by 2 1/3. So R capital R into 2 power 1/3. Okay. So this formula I am getting. So if I calculate volume, surface per bigger one, S equals 4 pi r square, smaller one 4 pi small r square. So 4 pi capital R into 2 power 1/3. Okay. Now if you can compare small s and capital S, so you can see this small s is having total surface area is larger than smaller s1. Okay, or I can write 4 pi r square, so square, so 4 pi r square 2 power 2 by 3. Okay, therefore S equals 4 pi r square means S into 2 power 3. Okay, so you can see this surface area increased for smaller diameter particle. Now why surface area increasing better? So whenever oxygen molecule will be reacting with any fuel, so it will be acting on the surface actually first. Okay, so surface part will be interacting with oxygen, and combustion will be occurring. And when combustion occurring, it will be exothermic reaction. When exothermic reaction happening, so surface part will be burned, then hot gases will be removed, and oxygen will be penetrating into the center part and it will be burning completely. Now if you have a smaller particle, the oxygen particle can reach quickly to the center part and it will be heated quickly. It will be reaching to your burning temperature or combustion temperature quickly. So combustion will be quicker, oxygen it is getting oxygen quickly, and again it is getting heated up quickly. Okay, that's why smaller particle is better, it will have larger surface area. So smaller particle means so you can see this pulverization definition. The goal of solid fuel pulverization to enhance combustion efficiency. Combustion efficiency means quickly the particle will be burning and it will be reacting with oxygen, and there will be possibility of not producing carbon monoxide or ash because it is getting proper oxygen, properly heated up, and complete combustion possible. Okay, surface area increasing and facilitating better mixing with air and promoting more effective combustion. Okay, this is the purpose of pulverization. So any coal fired unit or solid fired unit, they will have pulverization unit where they will be breaking the solid fuel into very small tiny particle, so that then it will be injected into the combustion chamber. So atomization, another term, will be there for liquid fuel system. Atomization enhances the combustion efficiency by increasing surface area of the fuel. The same strategy you can apply. Big fuel particle, as a diesel particle, you take and you break into smaller particles. Smaller particles have more surface area, So oxygen will be interacting on the surface, and temperature will be it will get proper temperature. It will be reaching to burning temperature quickly. Combustion will be quicker. So it will be better mixing will be possible, faster ignition also possible. Fuel injectors are commonly used to spray the fuel. So one nozzle type thing will be there. So the nozzle will be spraying the fuel. When it is spraying, actually it will be creating a very tiny particle, a small particle, that is called atomization. Okay. The fuel into combustion chamber, a form of a fine mist or spray, optimizing the fuel air mixture for efficient combustion. Okay, for efficient combustion, you are making very smaller particle, increasing surface area. Surface area increasing means oxygen interaction will be there. Temperature will be rising quickly. Burning will be proper. There is possibility of less possibility of producing carbon monoxide or ash or residual carbon, because it may have uh, sufficient oxygen to burn completely. Okay. Any boiler furnace system, they will have the pulverization system. If it is solid fuel is there or liquid fuel is there, then in that case atomization system must be there. Atomization system is simple, nozzle will be working, but in pulverization system you must have one ball mill to rolling element will be there. So there will be rolling element when solid fuel is passing through the rolling element, a heavy rolling element, so it will be breaking into very tiny particle. Calorific value. So whenever you are talking about fuel, so fuel will have calorific value. Calorific value means calorie term is there. You can remember. You may have studied in your school books. Calorie means unit measuring unit of heat, not temperature. So temperature measurement will be sensed in thermometer, but calorie you cannot sense. Okay. So quantity of heat energy released per unit mass, also known as calorific power. The higher the CV or calorific value, greater the amount of heat energy liberated per unit mass. Unit will be kilojoule per kg, and it can be different also. For example, calorie per gram also I can say. Okay. A worm calorimeter designed for constant volume measurement determine the heat of combustion of samples capable of burning the presence of oxygen. So normally this will be used for liquid or solid fuel. Okay. Now how to measure this calorific value, because thermometer can measure your temperature, but to measure calorific value, this bomb calorimeter will be there. What this bomb calorimeter like this, they will have one solid vessel, a diabetic vessel, actually very strong vessel it must be, it should not break, and it should have one lid. Okay, lid will be like this. Okay, now that is also solid vessel, so it must be closed properly, like pressure cooker you have. So lid will be closing strongly so that no air or fluid can go out. But in pressure cooker, normally in India use the heat loss will be there on surrounding, because this will be metallic. But if you insulate it properly, then that can be used as a calorimeter also, or bomb calorimeter also. Okay, so now you will have one stirrer. You have maybe water is there. Okay, and you take your sample here, this is called bomb. Okay, this is stirrer, and there will be one thermometer, meter, and there will be one electrical spark system. This will be electric. Okay, now through this channel there will be one valve. Okay, so you take fuel plus oxygen, and it will be controlled through this valve. Okay, the reactions that involves gas or oxygen, gas enters through this valve, gas or air enters, or oxygen through this valve. Okay, so inside this fuel plus oxygen is there, their reaction will be happening. So when reaction is happening, it will be exothermic reaction. Normally small amount of fuel you take, let's say diesel you take, wood, a small portion of wood you take, pulverized wood, mix with oxygen. Now initially you do not have temperature. I already told that to burn something you need three things, fire triangle I told already: oxygen, fuel and heat. Okay. So oxygen, fuel already you have, and you have to give heat or fire source. So fire source, you are creating one spark and you are giving fire source, then fuel will be burning. So it will be burning because of exothermic reaction, heat will be produced. Heat will be increasing the water temperature, because this is whole thing is submerged in water. When water temperature increased, you measure the water temperature how much increased using thermometer. Let's say 10 degree increased, okay, and you have, let's say, 500 milliliter water inside your system. Now 10 degree increase, 500 milliliter water was there. So then how much heat is there? So you can calculate Q equals MST, mass into specific heat of water, and T means temperature increase. Okay, using this formula, actually how much temperature heat generated you can calculate directly. So this is called bomb calorimeter, and the vessel must be adiabatic. No heat should be interacting from outside or inside. From outside heat should not enter, or from inside heat should not go out also. Okay. So this is the basic principle of your bomb calorimeter, and it is used to measure calorific value or amount of heat stored in a fuel. Normally solid or liquid fuel will be used to burn here inside the chamber. Now whenever you are talking about fuel, solid, liquid or gaseous fluid may be your natural gas, solid fuel may be your coal, wood, liquid fuel may be your petrol, diesel. So they will have lower calorific value, upper calorific value. In previous cases you measured calorific value only. I did not spoke about lower or upper. Now try to understand what is lower, what is upper. Lower calorific value or net calorific value or lower heating value is the mass of heat released when unit mass of fuel is burnt completely and the product of combustion are cooled to the initial temperature of the fuel. LCV accounts for the heat energy used to vaporize the water in combustion products, and it's generally lower calorific value. So LCV equals HCV minus some heat actually. Okay, so LCV is the lower one, because HCV will, when you're heating you're burning fuel, so your water molecule, if there is any water content in your fuel, so that will take some heat and it will be taking latent heat, actually sensible as well latent heat, and that heat actually you cannot use for your proper purpose, because whenever it is gaseous form it will be having this latent heat within it and it will go out. Okay, so that is not useful for you. Okay, so that portion you have to minus, then you are getting your LCV. Okay, so HCV or gross calorific value is or higher heating value is represents the total heat released when unit mass of fuel is burned completely. So total heat you are getting, and but you are not calculating how much water is there. Okay, whenever going calculating lower calorific value, that will be used for your engine calculation. Actually, engine how much power it will be getting. Higher calorific value may be very high, but some water content is there, so that is not giving you any value. So finally you have to take the lower calorific value, the digits, then you have to calculate further for system efficiency. Okay, ACV includes the latent heat of vaporization of water produced during combustion. So if any water particle is there, that also you have to consider here. It is their theoretical maximum value and is higher than LCV because it assumes that water vapor in the combustion products is not condensed and all the heat is recovered. But in LCV, more practical and application of water vapor combustion product can be condensed and the condensation heat recovered. Okay. A case study. Just one example. It is taken. Okay. So let's say one case study. I have three fuels. One is calorific. One is having calorific value 50 kilojoule per gram, and it is producing carbon dioxide and water. For example, I have, let's say, CH4. Okay, if you burn it, then with oxygen plus oxygen, so it will create CO2 plus H2O. Okay, I am not doing the balancing, how many water oxygen will be oxygen or methane will be required. I am not balancing it now. So in another case, I am getting carbon dioxide, water plus NOx also, plus sulfur dioxide also. Produce carbon dioxide, sulfur dioxide, H2 I can write. Okay, plus H2O plus CO2. So this one like this one this, and another I am getting CO2, produce only CO2 on CO, no, this is wrong, CO2 plus H2O. Okay, in one case I am trying to get, just some mistake is here, let's say CO. Okay, in first case I am getting CO plus CO also there. Second case I am getting NOx, SO2, H2O, CO2. In third case I am getting CO2 plus H2O. Okay, so which fuel can be better? Now you can see the calorific value is higher for A, lowest in C, but C is giving me carbon dioxide and water. Okay, so if you ask me to choose which is better, I'll take fuel C, because it is not giving me any harmful gases. Okay, fuel A is producing carbon monoxide, which is harmful. I told carbon dioxide is not harmful actually. Combustion engineer, all combustion engineers or researcher, they will try to produce carbon dioxide, not carbon monoxide. Okay, carbon dioxide is already there in atmosphere. Even we are exhaling also, sometimes we are inhaling also certain amount of carbon dioxide. Trees are surviving because of carbon dioxide, so that is not harmful, although greenhouse and other theories are there, so that we are not considering here. Carbon monoxide is harmful, so combustion engineer will target not to produce carbon monoxide. And fuel B, it is producing SO2. SO2 again it is dangerous. SO2 plus H2O, it will be producing acid. NOx, nitrogen 5 oxides will be there. NO, NO2, N2O3. So 5 oxides will be there because nitrogen has 5 valencies. So those will be creating harmful gases like nitrous acid, nitric acid. Okay, that is also not good for your environment. So fuel B also harmful. So I will not take fuel A or fuel B. I will take fuel C because it is giving only carbon dioxide and water. Okay. So in boiler case also, your target will be to produce carbon dioxide and to minimize SO2 or NOx production. Now in certain fuel, you have higher amount of oxygen. So what will happen? Let's say simple. I am giving you an example. CH4 is there, and oxygen very high amount is there. What will happen? It will be producing carbon dioxide and water. Okay, but it will not produce carbon monoxide because all the carbons will get enough oxygen and it will be producing carbon dioxide. So people will be happy. And when carbon dioxide is produced, the flame will be almost invisible, or bluish color some flame will be there. But if you have less amount of oxygen and you are producing CO plus CO2 plus other component, so CO is harmful. So and maybe some carbon particle also be produced. So if you see chula or rural people, they will be burning fuel, wood or something, so lots of black smoke will be coming. Black smoke, ash, it will be containing lots of carbon particle. So when carbon particle is there, it is possible that it will be producing carbon monoxide also. So that is actually harmful. But if you see oven, Indian oven or Indian oil, they are supplying gas to your household or kitchen. So normally you will not see any black ash coming or black soot coming from your oven. So that system is designed properly. So the whatever fuel is there, it is getting proper oxygen. So it is not producing any C or CO. It is producing carbon dioxide. Okay, so that's why the utensils will not be blackened. But if you see wood, someone is burning and some utensil is there, so that will be black because some carbon particle will get deposited on your pots. Okay, So that is harmful if you have carbon monoxide. Carbon dioxide also can deposit in your lungs, so that is also harmful. That's why smoking means smoke when you are talking about, that means it is having carbon particle, so it is getting deposited in your lungs, so that is also harmful. Stoichiometric ratio. Stoichiometric ratio or stoichiometric air-fuel ratio, the ideal or perfect ratio of a mass volume of air. So air and fuel. Okay, so this ratio you have to maintain. There's a certain amount of CH4 plus oxygen. You need certain CO2 plus H2O. I think you need 2 oxygen for 2. So 2, 2, and oxygen you need 4, 6. So 3, 2C, H4, 8, 4. Okay, now you can see this equation 3O2 plus 4 H2O. This proper amount of oxygen if you are giving, then your combustion is proper. You are not giving excess oxygen or lower oxygen. Lower oxygen, I already told that it can produce carbon or carbon monoxide, that is harmful. But what if I give more oxygen, so I will not produce any carbon monoxide, it will be good for environment. There is another question. Question is that when you are burning inside boiler, okay, you are giving air, fuel. Now you are giving extra air. Extra air means around 80% nitrogen you are giving about. Okay, and extra air you are giving means you are giving more nitrogen, which is not useful, and you are giving extra oxygen also. So what will happen? Extra nitrogen, oxygen, whatever is there, so that will take a certain amount of heat and it will be heated up and it will go out with your flue gas. Okay, so there will be heat loss if you are giving very high amount of air and you are thinking like, I will not produce any carbon monoxide, I don't want to harm my environment. So in that case you put lots of oxygen, finally your heat loss will be higher. So when heat loss is higher, your whole efficiency will be lower. You have to put more money for your fuel because you are burning fuel, but it is getting wasted because flue gas is taking lots of heat from your combustion chamber. So you have to give actually ideal air fuel ratio or stoichiometric ratio. That ratio you have to maintain. Now the scientist says like 10-20% extra fuel you keep, not too much. 10-20% extra fuel if you are keeping, then combustion will be complete and small amount of heat is going through this air, that is fine, but you are not harming environment and you are getting optimal efficiency. But if you are giving exact amount of air fuel ratio, then there is possibility that some carbon particle will not get burned completely, so they may produce carbon or carbon monoxide that can be harmful. So their suggestion, increase little bit, not too high, so 10-20% increase and you use it, that is fine. So you can read this now. Achieving the stoichiometric ratio results in the most efficient combustion when all the fuels is reacted with available oxygen, leaving no excess fuel or oxygen. Okay, but scientist says keep small amount of higher oxygen. Process heating equipment seldom operated in manner adhering strictly to the stoichiometric ratio. In this context, boiler and high temperature process furnace, a practical known as on ratio combustion is typically employed, which involve induction of modest excess air, modest, not too high. Okay, approximately 10-20% more than required to complete the combustion. So fuel properties. So fuel, first thing is viscosity. Okay, so if you have very high viscosity fluid, pressure drop will be higher. So whenever you are putting different viscosity fluid, you have to consider whole combustion thing, how things will work. In some cases you have to consider your flammability. Okay, flammability you need to know because of two reasons. One is that when you're storing, it should not burn quickly. So if there is a small fire source, it should not burn, and there will be not there should not be busting or any dangerous effect. And again, if you have lower flammability, it may be burning quickly in your combustion chamber. So you have to know your flammability. Some more thing you have to know, like flash point. Okay, some fuel will be flashing quickly, so that point also you have to know. Some cases you have to know pour point. Okay, these are given in your book D.A. Taylor. DATLM marine engineering book. Okay, just this theoretical thing, just you go through it. Okay, viscosity, flash point, pour point, these definitions, please go through it.